Hello, my name is Michael and I'm in the Mavrikakis group here in the Chemical Engineering Department at the University of Wisconsin-Madison. And today I'll be showing you some of what we do in our group and some of the resources that we have available to us. So to get things started, I just briefly want to introduce you to what we do here in the Mavrikakis group. And we specialize in the application of computational chemistry-based methods such as density functional theory, or DFT, to investigate material properties. In essence, we're able to model materials on these systems on our computers. And using these methods, we can understand and predict various chemical and physical properties. And so primarily in our group, we investigate solid interfaces for applications in heterogeneous catalysis. However, in our group, we do work on a wide variety of projects, such as chemical sensors and energy storage materials, just to name a few. And so a big focus in our group is being able to connect the calculations we make in our computers to things you can actually measure in experiments. And so one unique thing to our group is that we actually perform both experiments and calculations. And so we'll go through both of those today with several of the group members. But before we start with that, first we're going to enter our local cluster with Alan, and she'll show you where we make some of these calculations and discuss more details about our group.
Here in the Mavrikakis group, we modeled the structure of catalyst surfaces and of interfacial systems at the atomic level. At this length scale, matter obeys the laws of quantum mechanics. The Schrödinger equation is far too complicated for us to evaluate, but density functional theory, or DFT, makes several approximations so that we can study atomic systems. Even with these simplifications, though, we still need to use supercomputers for calculating the structures and energies of catalyst surfaces. Therefore, our group has access to a wide range of high-performance supercomputers, both at the University of Wisconsin and externally. Additionally, we have our own in-house supercomputers that belong exclusively to the Mavrikakis group, which combined have 41 teraflops of computing power. Our main supercomputers include Euclid and Thales, which contain over 100 compute nodes in total. And because these computers are owned by the group, that means that we can run our calculations efficiently and effectively without having to worry about what other research groups are doing on campus.
So like Alan was saying, we can use computers to calculate energies from our models, and we can compute things like reaction energies or activation barriers. Now, while these quantities can provide valuable insight into what's happening at a catalyst surface, they aren't something that you can typically measure directly from experiments. Usually you'd expect to measure things such as reaction rates or reaction orders. So really, we want to be able to have a more direct way to connect our calculations to experiments, not only to ensure that the systems we model are accurate, but also to understand why a material is active. And by doing so, we can use this information to design better catalysts. So our group has done a lot to find various methods that do just this, and two methods that we utilize quite frequently are Microkinetic Modeling and Kinetic Monte Carlo. And I might go into great detail, but essentially these methods allow us to use the energies we predict from our DFT calculations to compute experimental measurables such as reaction rates. Now, of course, we can only benchmark our calculations if we have reliable experimental data. So in our group, we work alongside a lot of world-class experimentalists, both here on campus and across the world. And as I mentioned earlier, we also perform some of our own experiments in-house. And so next we'll head over to Jake, who will tell you a bit more about those.
Hello, my name is Jake, and I'm a graduate student in the Mavrikakis and domestic group. And I wanted to give you guys a tour of some of the different experiments we do in the Mavrikakis group. Well, you may know Mavrikakis group as being mostly a computational surface science and catalysis group. We do, in some cases, build and then evaluate some of our computational predictions by doing intrinsic kinetic experiments. So, showing you one such case over here. This is a methanol synthesis reactor. It is actually a stepwise, we study this in a stepwise conversion, where here we flow in the liquid methanol that then gets evaporated by mixing in with helium, and then we can, through this online DC, FID, measure how much methanol we are producing, and compare that to some of the predictions based on the phase diagrams and active sites that we model.
In addition to using density functional theory and surface science to advance our understanding and discovery of new catalytic systems, we have also used our expertise in surface science and catalysis to develop new gas sensors, specifically the chemiresponsive liquid crystal sensor. This type of sensor can be developed to be cheap, lightweight, and requires no power in addition to being sensitive and selective. We perform density functional theory calculations to determine optimal active surfaces and liquid crystals to selectively detect new analytes for these materials. And we work with external collaborators to then evaluate our predictions and improve our models. Shown here is just one example where we show how we can use calculations to find cases where we can selectively detect ozone and chlorine gas without interference from other chemicals in air such as O2 or NO2. Our predictions are then validated by our external collaborators.
Hi, my name is Trent. I'm another graduate student in the Mavrikakis group, and here I'm going to highlight some of the impacts of the research products from the group. In total, Mavrikakis group publications have been cited around 36,000 times, and publications from the group currently garner around 3,500 more citations every year. We often publish in high-impact journals, as you can see in the lower portion of the screen from the list of selected publications. I was fortunate to work on the first publication in this list. This project related to the development of active palladium-based catalysts for methane oxidation in collaboration with the group of Professor Carnello at Stanford University and researchers at NIST. After people move on from the Mavrikakis group, they have many opportunities in both industry and academia. Group alumni interested in industry careers have gone to companies such as Dow, Shell, and AbbVie in recent years. Those interested in an academic career have gone to places such as Purdue University and the University of Houston. Others have gone to national labs, such as the National Renewable Energy Laboratory.
So thank you for joining us today. I hope you have a better understanding of what we do here in the Mavrikakis group. If you have any additional questions, feel free to reach out. There should be contact information in the following slide along with a link to our website. We hope you pick Wisconsin.